Professor Sturmfels. Professor Sturmfels is a very renowned name in the area of commutative algebra and algebraic geometry. And there are a number of areas which are basically started by him. And we have seen many during the last SIMPA school. Many of the areas, many of those topics were introduced by Professor Sturmfels. Professor Sturmfels is a professor of mathematics and computer science at the University of California, Berkeley, and moreover he's a very active director of Max Planck Institute. And if you get the chance to have a visit of this website, where lots of activities are happening, and there an advice to the youngster, this is really important to follow him on archive, because each and every paper of him by him is basically a beginning of some new research direction in the area of commutative algebra and algebraic geometry. And even today, he's going to unfold his recent work on partial differential equations, the connection of commutative algebra with partial differential equation, which is seemingly quite a new connection, which was not known, I think. As per my information, I'm not aware with, but this is again a brainchild of Professor Schrumpfels. So I'm going to we are really privileged to have you here. And today is a special occasion that Professor Sturmfels is going to be turning to 60 now. And this is his birthday. And this is a special seminar which is dedicated to his 60th birthday now. And over to you, Professor Sturmfels in Pakistan.
Okay, well, thank you very much for the kind introduction. I'm actually really happy to give a seminar on my birthday, and it's the best way to spend and to celebrate. Yeah, so the story I'm telling you is not quite a new story. So this gentleman who's shown there already thought about linear PDE with constant coefficients. I'll tell you who it is. But just in case there's anybody who is actually a PDE expert, this is really a talk in algebra and what I like to call nonlinear algebra. So let me shamelessly advertise a new book with Mateusz Michalek called Invitation to Nonlinear Algebra, and I'll make a specific pointer to this book in a moment. Let's start out with something very, very simple. I'm going to argue that a polynomial in one or several variables is exactly the same thing as a homogeneous linear partial differential equation, PDE, with constant coefficients. So homogeneous means a linear equation equal to 0. So in particular, in one variable, we think of polynomials as ordinary differential equations, ODE. So here's a calculus exercise. It's always good to go back to calculus. Suppose we want to find an unknown function phi in one variable z that satisfies this linear equation. The fourth derivative minus 6 times the third derivative plus 10 times the second minus 6 times the first plus 9 times the function is 0. Well, you all learn in calculus how to do this, right? So let me proceed as follows. I'm going to write this differential equation operator form. So delta stands for the operator of differentiating with respect to the variable z. And the bullet is just applying. So I'm applying this operator to my unknown function. Now the operator I can think of as a polynomial in one variable, and in every homework problem in calculus, polynomials factor nicely. So this polynomial factors nicely. It has a double root at 3 and then plus minus I. So from that, I can write down a basis for the solution. So since the ODE is linear, the set of solutions is a linear space. It's a 4-dimensional vector space. And I can simply write a basis by looking at the roots. So e to the 3z comes from the 3 because it's a double root. I also have z times e to the 3z. Then I have e to the iz and e to the minus iz from the last factor. And if I want to rewrite this in terms of real functions, the last two are just the trigonometric functions, sine and cosine I can take. So this is a basis for the solutions. So these are solutions, and every solution is a linear combination. So this is calculus. So let's go to upper division undergraduate analysis. So in upper division analysis, you probably encounter the one-dimensional wave equation. So I'm going to let C a positive real constant. I'm now looking for an unknown function phi in two variables, t for time and z for space. And the equation says that the second derivative with respect to t is equal to constant c squared times the second derivative with respect to z. Now, again, I can think about this as a polynomial in two unknowns, x1 and x2. Here it is in factored form. And based on this, we can write down the general solution. In fact, this was done almost 300 years ago. D'Alembert wrote the general solution as a superposition of traveling waves. So what you do is you take a function f in one variable that's differentiable enough, g, another function, one variable, and you write this equation, f of z plus ct plus g of z minus ct. So the two terms correspond to the two factors here. And then you check that this is a solution. And conversely, every solution has this representation. Now notice what happened here. So now the solution space is an infinite dimensional vector space. It's still a linear space, but now it's not finite dimensional. It's infinite dimensional, but nonetheless, we were able to write down just two simple expressions to encode our infinite dimensional solution space. Now, what happens at the special value where c is equal to 0? This is kind of interesting, right? We do like to take limits. So, well, if you just write down the traveling wave representation, then as c goes to 0, you do get a solution, any function of z. But that's not enough, right? Because you also need t times any function of z, but you can obtain that by a change of basis. So you can replace the second term by this difference quotient and then take the limit, and this exhibits the two-dimensional representation of the solutions. Okay, so we went from calculus to 18th century upper division analysis to early 20th century algebraic geometry. So Wolfgang Gröbner was very interested in foundations of algebraic geometry, and he argued that polynomial ideals play a big role, and he introduced differential operators to characterize membership in a polynomial ideal. He built on earlier work by Macaulay, and he derived such a characterization for zero-dimensional ideal. He envisioned this for all polynomial ideals, but he never quite completed it in his lifetime. And in particular, Gröbner wanted algorithms, algorithmic solutions, and this is what I'm going to talk in this talk. So here's a reference from 1938. So in English, this says on algebraic properties of solutions to linear differential equations with constant coefficients. So in spite of the very nice introduction that Imran gave, this is really not my idea. This goes back many, many, many years. Now, unsurprisingly, analysts made big contributions to this. In particular, in 1916, there was work by Ehrenpreis in the US and Palamodov in the Soviet Union, who studied our linear PDE. And a main step in their result was to characterize membership in a primary ideal by what they called Noetherian operators. So this led to a theorem called the fundamental principle, which I will explain. And this was published in two books that appeared in the same year, 1970. So Ehrenpreis' book is called Fourier Analysis and Several Complex Variables, and Palamodov's book is called Linear Differential Operators with Constant Coefficients. But before I'll explain the Ehrenpreis-Palamodov fundamental principle, let's go back. So this is indeed Wolfgang Gröbner. So this picture is not me. This is Wolfgang Gröbner. And in this book, in section 3.3, theorem 327, we precisely have this zero-dimensional case. So I said Gröbner knew the zero-dimensional case, and this is the theorem that Gröbner knew. So I'm going to go over this. So if I is a zero-dimensional ideal in a polynomial ring in n variables, so zero-dimensional means there are finitely many roots in n space. which we here interpret as a system of linear PDE. So today we think of polynomials as linear constant coefficient PDE. Then the space of holomorphic solutions has dimension equal to the degree of I. So this is exactly as in the calculus exercise. We also might ask whether they're non-trivial polynomial solutions. That happens if and only if the maximal ideal generated by the n variables is an associated prime. And we can use the algebra of ideals to identify the polynomial solution. So the m primary component in this case can be recovered by this ideal quotient. Whoops. So what happened? Sorry about that. Okay. So this ideal quotient, so we saturate I with respect to the maximal ideal, and then we do it again. And this gives us precisely the polynomial solution. So this is the textbook theorem. That was the case that Grobner knew. Let's move on to higher dimensional situations, and let's start out with prime ideals. So now P is a prime ideal in a polynomial ring in n variables. And here I'm going to assume complex coefficients. This means that the variety, the zero set of P, is an irreducible affine variety in n-dimensional space. So sometimes when I talk about prime ideals to people outside algebra, in the olden days, I used to say prime means very good, as in prime rib or prime time. Nowadays, I refer to Amazon prime. Prime means very, very good. So a polynomial f is in the prime ideal if and only if f vanishes on the irreducible variety. So we're going to replace xi by operators dzi, and we interpret as before the polynomials in P as partial differential equations. Now we begin with the remark that the classical solutions, the points on the variety, are known to the differential equation. They are encoded in the exponential solution. So as u is any vector in n-dimensional space, then we can form the exponential of the linear form, so spelled out here. So take the exponential function applied to the linear form with coefficients u1, u2 up to un. And this exponential function satisfies the PDE if and only if u is in the variety. So the PDE remembers the points on the variety as the exponential solution. However, remember the PDE is linear, so the set of solutions is a linear space. If I have a solution and Imran has a solution, then any linear combination is also a solution. So we can also take linear combinations of infinitely many solutions, right? This is not a finite dimensional space. And this is conveniently written in this integral representation. So for any point x in the variety, we look at this exponential function of z. Then we take more and more and more terms in the convex in the linear combination. And this can be expressed by saying we're integrating against any measure on the variety. So this gives us a function z, and this is a solution. But the converse proposition says the converse holds true. So any reasonable solution to this PDE arises this way, admits an integral representation of this form. So this is true for prime ideals. And again, let's give Wolfgang Grobner some credit. So he knew about this in the 1930s. Now, after primary ideals comes primary ideals. So they are a bit more subtle. So an ideal Q in the polynomial ring is primary if it has exactly one associated prime. In this case, the variety of Q is equal to the variety of that prime, so it's still irreducible, but you should think about this as fattening up the variety, right? So I start with my irreducible variety, maybe this curve, but now I make it fatter, I thicken it, and I have what a geometer might call a scheme structure on this variety. So here's the theorem of Ehrenpreis-Palamodov, the fundamental principle. So let's fix a prime ideal. Let's consider a P primary ideal Q. Then given this primary ideal, there exists a finite list of polynomials, B1 up to Bm, m polynomials, in two n variables, the nx variables and nz variables, such that the following integral representation holds for the solution. So what we do, again, we look at the exponential functions coming from points x in the variety, but now I multiply by my polynomial, bi. So I'm using the bi as a kernel. I integrate out x again, but now each of these bi has its own measure. So there are measures mu1 up to mu_m on the variety. So earlier we had one measure, now we take several, and then we take this linear combination. So the claim is that this is a solution. So the bi exists so that this is a solution, but more importantly, the converse is also true. Every reasonable solution to the primary PDE admits such an integral representation. So this is a direct generalization of this. So in this case, of a prime ideal, m is 1. We just have one integral, but here we have m over there. Now, what's the m? So the smallest m that you need can be written in terms of commutative algebra. So there's the 20th century abstract, let's say Atiyah MacDonald definition, that says you localize, you look at R mod P, localize that P, and then at M is the length of this local ring. Now, I now work at an institute called Mathematics and the Sciences. So as an algebraist in the sciences, I like the 21st century computational definition. So this is the definition I like. You go to Macaulay 2, you type degree, that's a positive integer. You type degree of P, that's another positive integer. The second divides the first, and the ratio is m. Okay, so this is the theoretical definition. This is the computational definition. Now, important is that these polynomials, B1, B2, so they're called Noetherian multipliers, they depend only on the ideal. They do not depend on the solution. So once per every ideal, once and for all, you compute these polynomials B1 up to Bm, and then they will serve as kernels to represent arbitrary solutions to the PDE, which is, as before, an infinite dimensional space. Here's an important example. So in the first version of this theorem, Ehrenpreis got it wrong, and then Palamerov gave a counterexample, and this sort of became an important example. And so let's take a line in three-dimensional space. So n is 3, and I take the vertical axis. I take the x3 axis. So the prime ideal is x1, x2. I'm going to put a multiplicity structure of order 2 on this line. I make a double line, and here's my primary ideal. So this is the ideal I'm going to look at. I'm going to take generators x1 squared, x2 squared, and x1 minus x2, x3. So this is a P primary ideal. Think of it as a double line. So here the red ideal written as a PDE for an unknown function phi in 3 variables, z1, z2, z3. So then I can give the general solution to this in the form that D'Alembert taught us. So the first summand is an arbitrary function of z3. So you check that certainly any function of z3 satisfies this. But then the second more interesting term is z2 times any function psi of z3 plus z1 times the derivative of z3. So any expression of this form is also a solution, and the converse says that all solutions come this way. Now, in this example, m is 2, so there are 2 Noetherian multipliers. We always have 1, and then the second one is z2 plus x3 z1. Let me just take a minute to show you how we can go from this polynomial in the z's and the axis to this representation by way of Palamerov-Ehrenpreis. I'm going to show you now how this theorem works. So first of all, well, the solution phi 1 that comes from the first operator, I just simply put the kernel 1 here. Then, of course, the measure is concentrated on the z3 axis. So a general point looks like 0, 0, z3. I have any measure here. I integrate out the x, and this gives me an arbitrary function of z3. So as I vary the measure, I can represent any reasonable function. More interesting is the magenta term. So here now I'm using the second Noetherian multiplier as the kernel. Put the kernel in. Then the rest is the same. I'm integrating against any measure mu2 on the line. So bilinearity, I have z2 times, so I can pull out z2 times this integral. I pull out z1, x3 remains inside because I'm integrating against this. But then you can check that this is a basic property of the Laplace transform. So multiplication by x3 inside the kernel corresponds to taking the derivative outside. And I get precisely this expression. Okay. So that's how the theorem works. And here's a very simple solution. Representation of the infinite dimensional space of solutions phi to this PDE. So let's summarize what we've accomplished. So we have these Noetherian multipliers, BI. They're polynomials in two sets of variables, the x's and the z's. The x's are integrate out. And given a primary ideal, they furnish a representation, a finite representation of the infinite dimensional vector space of all solutions. What we're now going to do, we're going to recycle these multipliers to answer Wolfgang Gröbner's question. Test ideal membership. So I'm going to switch the roles of x and z. So now I'm going to replace zi by the derivative with respect to xi. So I'm going to switch the roles. And I substitute inside the polynomial in two n variables. I replace z1 by dz1 and zn by dxn. Now, bear in mind that now these operators do not commute, right? So I have to be a little bit careful. And what I'm going to do is I take this polynomial and I move all the z variables to the right and the x variables to the left. So I expand this polynomial so that in every term, the x is on the left and the z is on the right. And afterwards, I do the substitution. So this gives me what's called the Noetherian operators. So these are now elements in the Weil algebra. So these are non-commutative, mildly non-commutative polynomials in the xi and dxi. And so they act on polynomials. So proposition is that these operators answer Gröbner's question. So Noetherian operators characterize ideal membership. Namely, a polynomial f lies in the primary ideal if and only if the following vanishing condition holds. Of course, fi, f of x, has to vanish on the variety. But furthermore, if I apply these operators to f and I get a new polynomial, these m new polynomials must also vanish on the variety. So membership in my thick line, in my thick curve, is characterized by a further vanishing condition. Not just f, but also these associated polynomials must vanish. So for example, suppose I like to use this to characterize membership in Palomodov's ideal Q. So this is the double vertical line. Well, a polynomial f has to vanish on that, but also applying our operator. So this is the second Noetherian operator to f that gets a new polynomial. That new polynomial also has to vanish. Now, I don't know what's the custom in this seminar, but if there are any questions, please interrupt me. Or maybe Imran will monitor the chat.
Yeah, there is nothing in the chat at the moment. Probably as soon as there will be any, I will interrupt.
Okay, let's take a pause. Huh? So here is the here's Palomodov-Ehrenpreis theorem from the 1960s, and then this is formulated for primary ideals, and it also answers the membership question. Now, what do we want to do on the algorithmic side, right? I mean, Wolfgang Gröbner wanted algorithmic solutions. Well, what we want is an algorithm, for example, that takes as an input generators of an ideal Q, and maybe I promise to you that it's primary, and the output are the Noetherian multipliers, the polynomials B1 up to Bm, or the corresponding elements in the Weil algebra. So here's some references. So in the zero-dimensional case, as I said, this is a standard thing. It really corresponds to Macaulay's inverse system. This was studied quite a bit in the computer algebra literature. In particular, there was this influential paper by Bernard Morin, but there are many papers that deal with this case. Interestingly, in the late 90s, from the control theory point of view, this was picked up, and there's a long and deep paper by Oberst called The Construction of Noetherian Operators. So he and Shankar came from control theory. Shankar published a paper, the Nullstellensatz for Systems of PDE. So this was the first works that raised the question, and they looked at Noetherian operators from a constructive point of view. I became aware of this, and I always thought this is a very, very nice way to think about polynomials. So I already included a very brief discussion of this in lecture notes on solving systems of equations from 20 years ago. But then the first actual algorithm that was implemented, that came in 2007 by Strupper and collaborators, so computational methods for the construction of a class of Noetherian operators. So they had a test implementation for a limited class in the system Cocoa at the time. But really things took off in the last 2 years. So there's work of the group of Anton Lakin. So they published a paper, Noetherian Operators and Primary Decomposition, together with Yaron, Sid Ruiz. They also have a Macaulay 2 package. So there was a lot of activity me and others were involved in. Much of what I say in this talk is in this article that just got published in the Glasgow Journal called Linear PDE with Constant Coefficients. And co-authors, Rida, he's a graduate student in Leipzig, and Mark, who is a student of Anton Lakin, who will join us as a postdoc in 2 months. So I will not describe the algorithm in full detail. I'll just tell you there is an implementation, a symbolic implementation in Macaulay 2 that you can try out, and I'll show you in a couple of minutes how you run it. So rather than talking about the ingredients of the algorithm, let me give you sort of a theoretical perspective that appeals to an algebraic geometry. So this is the current perspective from a more algebraic geometric point of view. So let's fix a prime ideal. Let's say C is the codimension, the height of the prime ideal. And let me also assume it's a Noether normal position. So it's R mod P is finite over the last n minus C of the variables. I'm going to write F for the field of fractions of the integral domain R mod P. So this is generated by the images U1 up to UN of the variables. And that's going to be what I call the big field F. F is the field of fractions. With that set up, the following 4 things are in bijective correspondence. A, P primary ideals Q of multiplicity M. So you fix an irreducible variety. You fix an irreducible curve, for example, in 3 space. Here's my curve. And you ask, what are all the possible ways of putting a scheme structure of multiplicity M on this curve? That's the first set. All the primary ideals that have that fixed prime for its radical. Second description is the punctual Hilbert scheme. So here's what I do. I form the formal power series ring in new variables, y1 up to yc. C is the codimension. But then I put the big field here. So there's a lot of action now in this field. And then I take the punctual Hilbert scheme. So this is the Hilbert scheme of finite subschemes of length m, locally at the origin. So it turns out that these 2 things are natural bijection. So it's kind of a way of localizing the situation. So the picture that you should have in mind is somehow I have my curve. I'm taking, perpendicular slices. In each slice, I have a fat point, and I can organize this fat point at the generic point. That's kind of the idea. Then there's a Macaulay's inverse system. So I can look at m-dimensional F vector subspaces of a polynomial ring in, again, codimension many new variables, Z1 up to ZC, that are closed under differentiation. And this corresponds abstractly to the Noetherian multipliers, our polynomials. And finally, the most important and most complicated description is the following. So you take the partial Weil algebra. So I start with the polynomial ring, and I only adjoin differential operators for the first C variables, for the partial Weil algebra. Now, this partial Weil algebra is an R module. It's both the left and the right R module. And I take the tensor product with the field of fractions, with the big field. The big field is an R module. That's how it came to us. And so this tensor product, I can either use the right module structure or the left module structure, and they're canonically identified. And I'm going to be interested in F vector subspace of dimension M that preserve this bimodule structure. So this is a very complicated thing, but this is really the correct way to speak about the Noetherian operators. So we published a paper with Jairon and Rosaire Homs called Primary Ideals in the Differential Equations, where this was one of the main theorems. So even if you don't care about differential equations at all, this is a very nice way of sort of organizing all primary ideals over a given prime. Let's go back for a moment to Grobner's problem. So Grobner asked the ideal membership question for an arbitrary ideal in a polynomial ring. I've given you a solution for primary ideals. Well, how can we go from primary ideals to arbitrary ideals? One answer is, well, let's do primary decomposition, right? Suppose we have an arbitrary ideal, and suppose we're given a primary decomposition, which is to say I is the intersection of k primary ideals. Well, you simply can parallelize the computation. You can pick out the Noetherian operators separately for each qi, and that gives you membership test. Or you can take the corresponding multipliers separately for each qi, and that solves the PDE. Now, this is a good approach if I has no embedded primes. However, in many interesting situations, there are embedded primes, and if they're embedded primes, we can do much better. And I would like to explain this. To illustrate this, let's take our double line again, and let's stick a fat point on this line. So here's my double line, and I'm going to intersect it with this point of multiplicity 4 at the origin. So in this case, the new ideal is this one. Okay? So the naive method, where I compute the operator separately here and here, would give 6 Noetherian multipliers, namely 2 for the line. Those are the ones we know. And then there are 4 obvious ones for the fat point. But it turns out that the double line eats up 2 of the 4 multipliers for the bad, but we only need 4. Right? So again, here are the 2 associated primes. For the minimal prime, I have the 2 multipliers and the corresponding operators. But here for this embedded prime, I only need 2 out of the 4. And these are the ones I use. So in general, this number 6 is a very, very big number. And this number 4 is a significantly smaller number. So to explain this savings, here is one theorem that I consider a commutative algebra theorem. It centers around the concept called differential primary decomposition. Let me explain this. So R is the polynomial ring. Now I is any ideal in the polynomial. I'm going to write P1 up to Pk for the associated primes, the associated irreducible values. Now, the philosophy of this talk is that currently, right now in 2022, we have an implementation that's a symbolic implementation in Macaulay 2, but the future is clearly numerical. We're going to set the stage here for accurate, reliable, certified numerical calculation. So I'd like you to think about these associated primes being given to us numerically as a test point in Bertini or a homotopy continuation in Julia. So then the differential primary decomposition is a list of k pairs, where each pair is the prime, pi, together with a finite subset, ai, of the Weil algebra, such that this gives the membership test. So the ideal is the set of all polynomials, such that delta applied to this polynomial vanishes on the ith numerically given variety for all delta in ai. Okay, that's the definition of a differential primary decomposition. I need one more ingredient here to quantify the complexity of this. This is the notion of arithmetic multiplicity. So the arithmetic multiplicity is the following. I take the sum over all associated primes of the multiplicity of the ideal along the prime Pj. As before, there's the 20th century theoretical Atiyah-MacDonald definition. And here is the 21st century computational Macaulay 2 definition. I'm just going to give you the latter. So for this multiplicity, what you do is you type this into Macaulay 2, so degree saturated. So the numerator is a positive integer. The denominator is a positive integer. The second integer divides the first, and the ratio is this multiplicity. Okay, and I add this up over all j. So the theorem is that the differential primary decomposition exists, and there's always exists one of arithmetic multiplicity, of length, of size. So what I'm trying to say is that the size, the cardinality of each AI is equal to this multiplicity. And this is also lower bound. So if Imran gives me any differential primary decomposition, then for each AI, this is a lower bound. Now, not only do we have this sharp lower bound, if this lower bound is attained, this differential primary decomposition is unique up to change of basis. So when you teach commutative algebra, you teach your students that primary decomposition is not unique, right? The primary components to the embedded primes are not unique. It is unique in this formulation. So differential primary decompositions are unique up to change of basis. Now, I should say a word about Yaron. Yaron is a brilliant young commutative algebraist. I believe his academic grandmother is in the audience. And Yaron really likes abstract commutative algebra. So I like concrete things over a polynomial ring, but in this paper that we wrote, the theorem is formulated in very vast generality, but at the expense that we have to work with the rings of differential operators, and they are very complicated. So if you have a ring that's not a polynomial ring, the Weil algebra gets replaced by a very wild non-Noetherian ring of differential operators. It works in characteristic P. It works for any commutative ring that's of essentially finite type over a field. And so there's a very general theorem, but as I said, I work on an institute that's called Math in the Sciences, so we'll stick to polynomials. Now here's how you do it in Macaulay 2. So Macaulay 2, you can compute a minimal differential primary decomposition, and so this computes the Noetherian operators and the Noetherian multipliers. You load the package. Here's a polynomial ring in 3 variables, x, y, and z. Here is the Palomorov's ideal. So this is now the axis, the double line with the fat point on it. Arithmetic multiplicity is 4. And then the command is called solve PDE. So solve PDE lists the associated primes. And for each associated primes, it gives a representation of the Noetherian operators. And this is the differential primary decomposition. So there are 2 for the minimal prime, and there are 2 for the embedded prime. So this was the double line with the fat point. So you can try this, and you can compute symbolically today in Macaulay 2 the Palomorov-Ehrenpreis representation of the infinite dimensional solution space by M, that is to say 4 little things like this. So this is the ultimate generalization of D'Alembert's result from 1740. Are there any questions? Maybe I should really pause.
Oh, so far so good.
So far so good. Okay.
Because everyone, I think, including me, are following the definition you are introducing and the computations.
Very good. Yeah. So if you got lost in some of the definitions, especially if there's students in the audience, the best thing is to compute. You go to Macaulay 2, you type in your favorite ideal, and you just say solve PDE and just see what happens, whether you can make sense out of it, right? So this example, of course, was this example. But let me make clear. So my main goal, and of course there are experts like Gleb in the audience on differential algebra. My goal here is not so much to talk about the Macaulay 2 implementation. This really sets the stage for the future. And in the future, this will be numerical. In the future, we will have this input, but then these associated varieties will be represented by a numerical representation of a generic point, which is what's happening in Bertini. And then there will be some linear algebra, but the linear algebra is subtle, right? Because what makes the linear algebra subtle is that we have a big field, right? You have to find a way of numerically working over this big field of transcendence degree n minus c over the usual field that usually works. So this is where the difficulty lies, okay? But it will happen in the future. Let me use the last maybe about 15 minutes. So as I said, I'll be quick today because I have to go to my birthday party. Let me talk a little bit about modules. So far we've talked about ideals. We talked about ideals in a polynomial ring, and we interpret this as PDE. And we talked about representing the solutions. Now, when you look at current textbooks or recent books in analysis that treat the Ehrenpreis-Palomorov theorem, analysts really are not so much interested in scalar valued functions. They're very interested in vector valued functions. In fact, they're not so interested in functions. They're actually interested in distributions. Okay. So what the PDE people really want is functions from n space to k space. And in real analysis, what people do, you look at functions from R to the n, real n space, to C to the k, complex k-dimensional space. So these are the fundamental objects in real analysis. Okay. And in fact, we're also interested in distributions from Rn to Ck. So here are two of these books that Björk has a very nice chapter. It's Björk's book on rings of differential operators. And there's Hermander's book called An Introduction to Complex Analysis in Several Variables. He calls it an introduction, but this is a pretty serious book, right? So sometimes students complain at Berkeley and elsewhere that studying algebraic geometry is hard, right? They say, well, you know, Hartshorne's book on algebraic geometry is really hard. It's very abstract. They're struggling with it. My latest response is, if you think Hartshorne is hard, try Hermander. I mean, once you tried Hermander, Hartshorne is easier. Okay, this is a very, very good book, not easy to read. Now in calculus, we started out today in calculus. In calculus, we learned how to rewrite one higher order ODE as a system of first order ODE, right? So the fourth order equation I had at the very beginning of the talk really is a system. You can think of it as a system, a first order system. Likewise, in algebraic geometry, we really appreciate matrix representations of geometric objects. We very much like determinantal ideals, determinantal varieties, right? That's also in commutative algebra. The varieties we like best are those that are given by rank constraints on matrices. Determinantal varieties are the ones we like best. So therefore, it's quite natural to pass to modules, right? So in the first part of the talk, I spoke about ideals. Ideals represent schemes. We can think about this as PDE, and then the solutions to these PDE endow the scheme with the nice geometric structure. But now we're dealing with modules. So ideals are to schemes as modules are to coherent sheaves. And in this talk, all my sheaves are an affine space. I mentioned Yiron and many people like abstract things. You can have sheaves on other spaces, but today in the next 10 minutes, I will talk about modules over a polynomial ring, that is to say, coherent sheaves on n-dimensional complex affine space. Okay, so now we're looking for such functions. Now PDEs that describe such functions. So let's say I have a system of L linear PDE that constrains the function psi. This is now represented by an L by K matrix, which I call A, with entries are polynomials in n variables. So now I have a matrix with polynomial entries, L rows, one row for every PDE, one column for every dimension in the target space, and the entries are operators in n variables as before. Let me write M for the submodule. So R to the K is the free polynomial module, and I look at the submodule spanned by the rows of A. And such a submodule has a primary decomposition. Okay, so I can write M as an intersection of primary modules, M1, blah, blah, up to MS. Actually, when I got into this project, what I found quite interesting, in the computer algebra literature, there are many, many descriptions of the primary decomposition for ideals, but almost none for modules. So when you study commutative algebra abstractly, say from Eisenbach's book, you immediately do this for modules. But on the computer algebra side, people have not dealt with modules a lot. In fact, the most recent implementation of primary decomposition is quite new. But our code, so as I said, largely Anton Laken's code for solve PDE, also computes differential primary decompositions for modules. And here's an example at the top. So here is a matrix. It's this matrix. Actually, I wrote the transpose. So it's this matrix. So I'm looking for unknown functions from 4 space to 2 space. So this has 2 coordinates, psi1 and psi2. And I'm interested in this system of 3 differential equations. Okay. So these 3 differential equations are the rows of this 3 by 2 matrix. So the first row is the first differential equation, second row is the second equation, and so on. Right? Now, how do we solve this? Well, again, the students in the audience, don't worry so much about the theory. You go straight to Macaulay 2 and you write these 5 lines. So R is the polynomial ring in 4 variables. That's the 4. Then you write this matrix. M is the image. So here, I took the row space, and Macaulay 2 likes the column space. That's why I took the transpose. You say arithmetic multiplicity, answer comes back 9. And then you say solve PDE, and this gives you a D'Alembert type representation of all solutions. So this example is already quite interesting. So this module has 6 associated primes. The first 5 are just these very simple monomial primes. And the last one is the twisted cubic curve. So I once learned from Dave Beyer that especially in Eisenbach seminar, every talk in Eisenbach seminar has to have one example, and it's always the same example. It's the twisted cubic curve. So if you give a talk in this field, you have to somehow sneak in the twisted cubic, and here it is. P4 and P5 are embedded, and then P1, P2, P3, and P6 are minimal primes. The multiplicities are 1, 1, oops, the multiplicities are 1, 1, 1, 1, 4, and 1, so the arithmetic multiplicity is 9, right? So the output looks a little bit more complicated, I'll spare you, but it's very simple. You just go to Macaulay 2, and now you can do this for any ideal, and in fact, for any polynomial module, any submodule in a free module over a polynomial ring, or geometrically, any sheaf, coherent sheaf on affine n-dimensional space. Now, in the last couple of minutes, I'd like to talk about, go back to control theory, and going to say a few words about syzygies, and then I'll talk about my latest paper in the area, and then the time will be up. So A is now the matrix we have. So now A is this K by L matrix, and we interpret this, again, this is a system of L PDE for an unknown function from n space to k space. Let's calculate the kernel of A. So the first syzygy, so I'm going to write the kernel as the image of another matrix B. So B is a K by K prime matrix. Okay. So I claim the following 4 things are equivalent. The first thing is I can take the transpose of this little sequence and it stays exact. Now, in general, this is not exact anymore, right? Over a polynomial ring, if you have that the image of B is the kernel of A, and you take the transpose, well, the image of A transpose is contained in the kernel of B transpose, that they may or may not be equal. Okay, so one says they're actually equal. 2 and 3 are easy commutative algebra reformulation. This is equivalent to saying that the module that we're interested in, the image of A transpose, is a zero primary module. It's primary to the zero ideal. Remember, this cannot happen for ideals, okay? This can only happen for modules. Another formulation, part 3, is the quotient of R to the K mod M is torsion-free. So I take mod M, it's a torsion-free module. And finally, the PDE interpretation, the PDE given by A admits what's called a vector potential. It's controllable, what the control theorists call controllable. And in English, every solution to the PDE is obtained by applying the differential operator B, the kernel, the syzygy operator. Let me illustrate this for this example. So this was the example we just had that we ran here in Macaulay 2. So here in blue is the differential equation. I'm sorry, let's take this differential equation. It's a different one. And here, this is the matrix A, very, very simple. And then the kernel of A is spanned by the columns of B. Right? So the kernel over the polynomial ring is minimally generated by the 4 column vectors of this skew symmetric 4x4 matrix B. Now, and this is a controllable example. So in this case, the theorem holds. So what I'm saying is the following. You can make solutions. You can solve this PDE as follows. I take any function whatsoever. Let me pick somebody in the audience. Okay, so Alicia. So Alicia gives me any function whatsoever in 4 variables, say differentiable. Then I apply, and then I pick any column, anything in the column space of span of B. I take maybe the 3rd column. Right? Then I apply the 3rd column to Alicia's scalar function. Then I get a vector of 4 functions. I call these functions psi1, psi2, psi3, and psi4, and this solves the differential equation. That's easy, but under this hypothesis, all the solutions come this way. They come from vector potential. So this is very, very nice, right? Analysts like this, control theorists like this, so you can build designer solutions. So Alicia can design her function. She can choose it to have compact support. She can make choices she likes. She can pick a distribution she likes. And then I can take her designer choice and make a solution to the PDE out of the designer choice. So compact support and waves. So if these nice things happen, so if the PDE admits a vector potential, then we can build solutions with compact support. And the converse holds as well. So the following converse holds. The PDE admits compactly supported solutions if and only if the zero ideal is an associated prime of our model. I learned about this theorem from more recent work of Shankar. So he has some beautiful lecture notes called controllability and vector potential. So I mentioned this because this really brings in syzygies in a very, very direct way. Now, analysts are interested not so much in classical solutions. They're very interested in distributional solutions with very, very low dimensional support. And they're interested in wave solutions. They're interested in solutions that have qualitatively the behavior that we saw in D'Alembert's traveling waves from the 18th century. Jonas Hirsch is a local analyst. He's a professor of the calculus of variation at Leipzig University. And we got quite inspired by this paper he wrote. He published in 19 called Dimensional Estimates and Rectifiability for Measures Satisfying Linear PDE Constraints. There are 3 co-authors. So De Philippis is quite prominent. He's quite a prominent analyst at the Courant Institute. So this is a serious paper in calculus of variations. So we got talking to them, and we ended up writing a paper together with Jonas. So this is Mark, Jonas Hirsch, and myself, and we wrote a paper we posted recently called Making Waves. So we just developed algebraic tools for constructing wave solutions and for constructing distributional solutions with low dimensional support. So these are not the classical solutions that I was interested in, Grobner was interested in. These are solutions that are of interest, current interest to PDE people. Maybe on a personal note, the city I am in, Leipzig, is very much a city where analysis is very strong. It's really a PDE place. So part of the reason I got into this collaboration is a little bit like when you travel to Rome, you do what the Romans do, right? So if you travel to Leipzig, you do PDE. So that was one of the motivations. So what's a wave? Well, first of all, a simple wave is simply a trigonometric function. Remember, we're interested in functions from n space to k space, real n space to complex k space. And a simple way to make such a function is as follows. I take the exponential of ix times the dot product of xi times x, and then I multiply, this is a scalar, I multiply it with the vector u, and I is the square root of minus 1. So here xi is a real n vector called the frequency of the wave. And u, so it's a real n vector, and u is a complex column vector of length k called the amplitude. So wave has a frequency and the amplitude, and given a frequency and the amplitude, I can make such a function. Now, we could ask, to what extent simple wave solutions exist for a PDE? And there's again a variety that characterizes it. So this wave will solve our PDE if and only if a of xi, so this is my matrix. This is my matrix of polynomials, and I substitute the frequency vector in. So this is now a real k by L matrix. I multiply this with this column vector, and I get 0. Sorry, L by k. It's a real L by k matrix. U is a column vector of length k. So I'm interested in the bihomogeneous variety given by this equation. Now, generalizing from simple waves, I'm going to say a wave pair is a pair u pi, where u is the amplitude vector, and pi is now a linear space of r to the n, such that a times u is 0 for all xi in that linear space. Now, a classical wave solution is any superposition of simple waves where the frequencies lie in such a pi. So that's called a classical wave solution. And by a wave solution, I mean any distribution that's a limit of such classical wave solutions. So I'm inside the space of tempered distributions, and I take a limit of classical wave solutions. So there's simple waves, and there are classical waves, and then there are distributional waves. Let's see this in our example. So we studied the first order PDE very much, where the entries are linear forms. So in this case, the variety that I alluded to in the previous slide is naturally in the product of projective k minus 1 space for the complex column vector. Pi is now a point in the Grassmannian of R space and N space. The projection of this variety into the first factor is what the analysts call wave cones. And the study of these varieties really generalizes objects that are beloved in algebraic geometry and commutative algebra, such as determinantal varieties and Fanos. So for example, let's look at our PDE here. So I can take this matrix times this column vector. I can swap the roles of xi and u. I can rewrite it like this. And so this is a surface in P3 with coordinates u and P2 with coordinates xi. I'm here projecting onto the u, recovers the twisted cubic. Here it is again. And so for every amplitude in the wave cone, we obtain distributions that have very, very small support, that are supported on a line, and they satisfy our PDE. Okay. So time is up. Let me close. So this picture that you see, this yellow-red picture, is the logo of the nonlinear algebra group at MPI. To the south in India, this would be called a Somosa. I'm sure in Pakistan, there's the analog of a Somosa. So this is a tetrahedron that you blow up, you puff a little air into it, you fatten up the tetrahedron as these 4 singular points, and then you have in red the unbounded elephant ear. So this makes up Cayley's cubic surface with 4 singular points. Now, algebraically, this is the determinant given by the determinant of this matrix of linear forms. But this matrix, like every matrix you see from now on, if you see a matrix filled with polynomials, I like you to think about this as a PDE. So what I'm trying to say, this picture is a PDE. This picture algebraically is the determinant of this 3×3 matrix. But this matrix really is a PDE for an unknown function psi from 4 space to 3 space. Now, if this picture is a PDE, how can we make solutions? Well, what you can do today, you have a symbolic implementation in Macaulay 2. So you go to Macaulay 2, you form a polynomial ring in 4 variables, you type in this matrix, and you say solve PDE. And then you look at the solution. Now, the discussion about waves and wave cones was a little fast. So let me again advertise, we have this paper that we just posted called Making Waves. It contains all the details. And with that, I apologize for going 90 seconds over time, and I thank for your attention.
Thank you, Professor Sturmfels, for wonderful lecture. So okay, there is one question by Ziegler, Martin Ziegler. Can you comment on the computational complexity analysis of this approach?
Yeah, we have not done a computational complexity analysis. So as I said, the current algorithm, so I should maybe say a word about this. So this, at the moment, the implementation relies, so under the hood, so when this algorithm gets called, we're still using a built-in version of primary decomposition. So we're using built-in Macaulay 2 code for computing the associated primes. So the difficulty is at least as large, and that in most implementation relies on Grobner bases. So we have not done an analysis. I would expect in the worst case, it's similar to the double exponential behavior of Grobner bases. On the other hand, in geometric situations where things are probably better, and in the future, when we aim for numerical implementation, Professor Ziegler, not only will we have a complexity analysis, possibly more important, we have a condition number analysis. In numerical computing, it's not just the bit complexity, but it's really the conditioning that will play a big role. But we have not done that in our work.
Okay, Professor Sturmfels, I have a question. Do you see the work of Maurice Janet, what he has given regarding to the Janet basis in order to solve the Maurice Janet?
Yes, so Janet bases are important in differential algebra and more general different. So from the point of view of differential algebra, what I did is a very, very trivial special case. So I really spoke about the commutative case, really.
Yeah.
I reinterpreted just calculations in the usual polynomial ring. Now, of course, you can do Janet bases also there, and some people have done that. On the other hand, the real power, I think, of Janet bases is for nonlinear PDE, more general differential algebra. And so I have not looked at that. So Janet bases, there are other bases. There's something called Thomas decomposition. If I were to pick on somebody in the audience, it would be Gleb Pogudin, who could answer this question much better than me.
Philip, would you like to speak?
Maybe off for a coffee.
Yeah, probably.
Yeah. You hear me?
Yeah, we can hear you now.
Any comments on Janet bases?
Yeah, so I have to say I don't see an immediate connection in a sense, because to the best of my understanding, Janet basis is a way to organize initial monomials of the ideal in a good way, right? So that not they all are of the same type, they all are initial, but some of them are initial because they are got by multiplying by this or multiplying by that. Of course, we can interpret this in PDE sense, but I cannot come up with a like analytic meaning of that. So I don't know. I understand what you are pointing at, and indeed there may be a connection, but not off the top of my head.
Okay.
But
okay, thank you.
Since you unmuted me, many thanks to Bernd for the wonderful talk, and happy birthday.
Thank you.
Yeah. It is really a wonderful talk, loaded with a lot of definition and many enticing connections, and I think a lot more for everyone to explore. Anyone in the audience with a question, you can simply raise your hand. We will unmute you. Okay, has anybody extended Liouville's theorem, differential algebra, to general PDE solution in closed form?
Oh, that's a very, very good question. So this is more, goes in the direction of differential Galois theory, which I have not studied, but I think it would be very interesting to look at in this connection, to sort of move, look at differential Galois theory, both for, even in this simple case, I think would be interesting. I have not done that.
Mm-hmm. Any other question? Okay, everyone is settled. All the questions are settled, and a lot more to study for everyone. Once again, okay, Sarah has a question. I'm not sure if this is the right question to ask. She's a numerical analysis expert. I was wondering if these basis function can be used as a activation function for a way of solving the PDEs.
I don't know, but I think it's a very good idea. I think, deep neural networks is really an opportunity to bring all mathematical tools to bear. We're having a workshop actually in 2 months here on differential algebra, and there will be one talk, or maybe even 2 talks with the connection to machine learning and data science. So I don't know, but I think it's a good idea to try.
Mm-hmm.
Go for it.
Yeah, Zara, you can unmute yourself. Yeah.
All right. Hello. So I was just wondering, because I mean, currently I'm not an algebraic person or a commutative algebra person at all. So this might come across as a very naive question. But currently, most of the activation functions are based on the interpolation basis for how these polynomials are represented or things like that. So I was just wondering if these bases are better conditioned, firstly, of course, for it to be used numerically, and whether this would make sense. Has anyone done this work before?
Yeah, well, so I would say let me turn the question around. Can we think of scenarios where we have linear PDE constraints, on the activation functions of a network, right? So maybe from the application, from the learning properties we want, there might be some constraints, right? If that is the case, then maybe these techniques could be useful. So I think it's not so much that I would, come up with the PDE and provide a basis and then you can use them. I would say if there are constraints, if the matrix A somehow comes from the application, and I think that's possible because, as I said, control theorists are very, very interested in this. So I would say at the interface of control theory and learning, this might be possible. I haven't looked at it, but it's a really good idea.
But maybe this leads me to another question, and that is there any indication on whether the choice of these basis functions is better or worse than the ones that people have already been using before?
Well, I don't think that. So remember, what I'm speaking about here is an infinite dimensional space, right? So I'm giving a basis, quote unquote. I'm using higher algebra. I'm using nonlinear, commutative algebra to give a basis of m things for an infinite dimensional space. And in that sense, so I think maybe the way to think about it, let's go back to, let me put this up one more time. I think about D'Alembert, right? What would you do with this equation, right? So this is the equation. So maybe from some physical situation, you might be that in your neural network, the activation function should satisfy this. You could imagine that this might be the case. Then what I'm saying is that every function has this representation. I have a basis, quote unquote, of 2 things, right? This is the first basis thing, and this is the second thing. But of course, f and g can again be arbitrary functions. I'm just giving you a structural result that, so I'm not really talking about a finite dimensional vector space basis in the usual sense of numerical linear algebra. I am afraid I have to run. So there are some people
Yeah,
waiting
yeah.
for me downstairs.
Yeah,
I would
we can
love to
understand.
stay. Thank you very much for coming, and thanks for the invitation.
Thank you, Professor Sturmfels. It was wonderful. It is wonderful to have you here. Happy birthday from our side,
Thank
and
you.
many best wishes from Pakistan and from all over the world
Bye,
on
and
your
I hope
60th
to be
birthday.
able to visit before too long in person.
I hope very soon.
Bye.
Bye.